Good morning, everyone. My name is Angel. I'm a PhD student at Stanford. It's a great honor to be here today to share my research project with all of you, which is to elucidate the effect of support acidity using platinum nanoparticles on propane combustion. The motivation of this project is that we hope to combust propane because propane belongs to one of the volatile organic compounds which are harmful to human body, environment, and ozone. Not only that, propane also forms the hydrocarbon emission. This figure shows the emission from the on-road vehicles in the past several years, and you can see it gradually decreases, mainly because of the more rigorous Environmental Protection Agency. This is great because we hope to eventually reduce this emission to zero. However, to do that, we hope to still rely on the advance in the catalytic converter, which is able to convert the harmful hydrocarbons into less harmful products, CO2 and water. And the very first thing we hope to study, this reaction, is to look into the literature, try to identify the best elements for this reaction. And from the literature, we have found out that palladium and platinum are best elements because they are very good at breaking the CH bond, which is the rate limiting step for this reaction. From these two figures, you can see that people have found out that this palladium and platinum is able to outperform other metals for methane and propane combustion. However, the price of the palladium and platinum are very expensive, especially because most of the metals are used for catalytic converter. If we're able to find a way to try to find the active site for this reaction, we're able to engineer the site and eventually optimize the usage of noble metal. So in order to do that, we have focused on our first parameter to study, which is to determine the best ratio of palladium and platinum. So here, what I'm showing is the microscope images for 5 different ratios palladium and platinum, with all the size changed from or ranging from 2 to 3 nanometer. So with this nanoparticle, we have deposited them onto thermally stable alumina support, and you can see that the particle shape and size is mostly maintained after the deposition. So now with this set of well-defined materials, we are able to study the activity. So we have exposed the catalyst in the propane combustion mixture and used a ladder curve to study the performance of them. So here what I'm showing is the T50 for the 5 different ratios. And basically the trend is that when the platinum content increases, the T50 also decreases. So platinum is the best ratio for this set. And not only on alumina, we have also found the same trend on all other different supports. And so from here, we have found out that the pure platinum is the best ratio among all the palladium and platinum ratios. So now this is the effect of the palladium and platinum. We are also very curious about the effect of support. So we have focused on platinum and study the support effect for this. And basically from the ladder curve again, we have found out that this tungsten doped titania, it is able to outperform all other supports. And from the kinetics measurement, we have confirmed the trend where this tungsten oxide is indeed more active. And from the literature, we have found out that it's mostly because the tungsten-doped titania has a higher fraction of the bronzite acid site that usually plays an important role for propane combustion. So in order to solely study this support effect, we hope to now focus on changing the amount of the bronzed acid site to see whether there's indeed a trend associated with that. So we have now solely focused on the 2 nanometer platinum and deposit them onto a variety of different acidic supports. Here we have chosen the silica alumina support because by using different amount of the silica, we are able to tune the surface fraction of the bronzed acidity. And because we hope to expand the library a little bit, so we have also deposit different amounts of the tungsten oxide onto this 30% silica alumina in order to create even more acidic support. So now we have this 8 different samples in this library. We again study the activity of them. So what I'm showing here is the Lidl curve and the kinetics measurements for this 5 different samples. That is the silica alumina set. Basically, you can see with the increasing amount of the silica or the increasing degree of the support acidity, you see an increase in the activity, not only in Lidl curve, but also in the kinetics measurement. And we have found out that with the dopant of the tungsten oxide, the acidity is further increased as well as the activity. So we have successfully found out that this bronzed acidity is indeed a very important factor for this reaction. So now we hope to ask why this bronzed acidity is playing this important role for propane combustion. So we have now chosen hope to study these several different factors to try to find that what's the factor that is in line with the support acidity. So firstly, it's possible that the change in the metal dispersion for different support will have different activity. However, the fact that we used nanoparticle is able to help us have the constant surface area of the metal. So we should have the same metal dispersion across different samples. And it's also possible that the support is participating in this reaction by mass van equivalent mechanism. However, the silica alumina is an inert support, so it should not really participate in this reaction. It is also possible that the reaction mechanism is changed in some way. However, we didn't see any change in the activation energy in our prior slide. So we do think that the reaction mechanism, or at least the activation barrier, is maintained across different samples. So later on, there are still 2 other factors we hope to examine, whether there is a change in the active phase or there's a change in the type or number of the active site. So to examine the oxidation state, we have used XPS on the before-after catalysis catalyst. So we have used XPS on this platinum on alumina and platinum on the silica alumina, and found out that basically the platinum's oxidation state is maintained before and after catalysis. So the change in the oxidation state should not be a reason for this support effect. And next, in order to know whether there's any change in the active site or any change in the type of the active site, we have used rate order to examine how the metal interact with the change in the reactants. So in our reaction, we have 3 different reactants: propane, oxygen, and water. And basically, if we are just looking into the effect of the palladium to platinum, we see that when the platinum content is increased, the propane rate order becomes more positive, whereas the oxygen rate order becomes more negative. This is mostly due to the change in the surface chemistry, where it makes us believe that the fraction or the active site, the type of active site is changed, and which is able to help us measure the property that is corresponding to the change of the active site by the rate order. However, when we look into the rate order on the platinum on different supports, we see that the rate order for propane and oxygen remain unchanged. So from here, we believe that the number or the type of the active site is maintained across different acidic samples. However, from the water rate order, we have found something interesting. From here, we see that when the support acidity increased, the water rate order becomes less negative. And also we have seen that turnover frequency in the dry and wet conditions is also changing in different acidic samples. But basically, the takeaway is that when the support is more acidic, the water poisoning effect is less pronounced. So this is very interesting, and we do believe that this is a very important factor that is in line with the change in the support acidity that is able to help us identify the role of the acidity here. So we have conducted several different tests to focus the water's role, and eventually what we have determined is that water is solely or mostly an inhibitor for this reaction by blocking the active site for platinum. So we have now hoped to focus on whether there's any different water coverage on the platinum site. So we have looked into the literature and found this module, which is able to help us simulate the water coverage on the platinum site. So we need to make several assumptions beforehand. Firstly, we assume that this rate is mostly a first order with respect to propane and zero order to oxygen and CO2. And then by expanding this rate, we can rewrite the formula by expanding the rate constant formula and the site of the platinum into this following form. And eventually, we are able to reach the final chemical formula here, which is that the rate is solely depends on the conversion and the propane pressure and the water constant here for this reaction. And then eventually, what we can do is that we can use the data in the dry kinetics and wet kinetics to determine several different parameters here. And basically, this is how we do the procedure. Not only conducting the kinetics measurement in the wet condition, we have also do the measurement in the dry condition and found out that the trend for different acidic samples is maintained, with the degree of the activity difference decreases in dry condition. And with this information and bringing this information to the formula, we're able to eventually reach this following figure. Basically, from this figure, we can see the water coverage on the platinum site, where firstly, as the temperature increases, the water coverage is decreased, which makes sense because higher temperature will make the water unstable at the surface of the platinum. And what more interesting is that with increasing of the support acidity, the water coverage becomes decreased, which is something that is less intuitive, because more acidic samples should have a higher fraction of the bronze acidity, which is able to attract the water. However, the fact that this water coverage is on platinum, so it's possible that this more acidic sample is help converting the water to the support and make the platinum free site exposed to do the propane combustion reaction. So with that, we have found out that the support acidity is indeed playing an important role for propane combustion. And when the support acidity increases, the degree of water poisoning decreased. And then eventually, using the model, we have found out that the water coverage on the platinum is decreased with an increase in support acidity. And with that, I hope to thank all of our collaborators, and I'm happy to take any questions.